recording this. This is now a good start, good moment to start. Okay, so let me see. I'm sharing the screen. So welcome everybody to this. Let me see. I'm trying to get my screen shared. Okay. Here we go. So I hope you see my screen. So as I said, welcome everybody again to this lecture on data science. Today the plan is to finish the examples that I had about non-negative matrix factorization that we started last week or last time this week, and then we move on to self-organizing maps. So that's the second part of this lecture is going to be about that. So just a quick reminder what non-negative matrix factorization means. So suppose you have a matrix X comprising your data. So the columns are vectors of data. And so you want to represent your data in a low dimensional space in such a way that the feature vectors that characterize your data are interpretable in the sense of the data attributes themselves. And in particular, if your data are positive, so you have positive attributes, you know, age, income, that sort of thing. So you want that when you are decomposing your xj in components, so you approximate your xj by a linear combination of some feature vectors w, you want that all these coefficients are non-negative. And so that means that you are factorizing your x in a low rank product of two matrices, which all have non-negative entries. So that was what non-negative matrix factorization is doing. And the contrast with the singular value decomposition is that singular value decomposition seeks to find feature vectors which are orthogonal, but orthogonality is a little bit problematic from the point of view of interpretation, because orthogonality typically leads to components which are negative, because you see the inner products have to cancel, and so you have to have negative and positive contributions typically. So therefore the approximation is different. It is non-orthogonal.
Good afternoon.
Good afternoon. And so the approximation has to be calculated differently, and so that was the topic of last time's class. And so we had some examples, and in particular this example was relevant for my next application. So if you choose the rank to be low, so you are trying to represent your data in very few feature vectors, in terms of very few feature vectors. So then you can say that these feature vectors are somehow giving a summary of what your data is about. So if you want to have a quick glance what's in your data, try to make non-negative matrix factorization and then look at the feature vectors. And typically these feature vectors are capturing the main features of your data. And so the example here was that I took a sample of handwritten digits which contain only 3s and 7s. And when I do the non-negative matrix factorization, I find these 6 feature vectors. And when I'm looking at those feature vectors, I realize that 2 of the feature vectors look like a 3 and 4 of them look like a 7. And it turns out that in fact approximately one third of my data vectors were indeed representing handwritten 3s, and 2/3 were representing 7s. So you see how these feature vectors nicely capture the contents of my data. So the take-home message here is that if you need to have a quick look on your data, you can do the non-negative matrix factorization and just skim through your few feature vectors, and you see more or less what's in the data. I will give you another example soon, But before that, I talk about this example that I started, which was I call it community detection, and I realized there is a typo in the title, so there should be two M's, of course. So we are looking at a network. A network consists of vertices and edges. So V is the set of vertices and E is the set of edges. And edges are non-directed edges here, so you can go both ways. So you can use the edge to jump from node to another using the same edge. And so what is the application that I have in mind here? So one of my research interests is related to brain. Okay, and so there is a big interest in understanding the connectivity of brain. And so what does it mean? It means you want to find out which brain regions are communicating with each other. So the white matter consists of these axons which are connecting different parts of the brain. And so when you give let's say a visual stimulus to a person, so what happens is that the visual cortex is first activated, and then the visual data is processed by, let's say, frontal cortex. And if the visual stimulus is such that it makes you think about muscle movement, your brain may also activate the motor cortex. And so you see that these three brain regions, visual cortex, frontal cortex, and motor cortex, are connected to each other. So now, if you use functional brain imaging, you will see activity in one brain area, you will see activity in another brain area, you will see activity in a third brain area. And so you may conclude that these three areas are connected, and the connectivity question is exactly which brain regions exactly are connected. So you can think that my network is representing brain, and those dots are representing different brain areas. And what I'm trying to do here, I'm trying to figure out which brain regions are connected to each other. And so in this example, I have a 36 node network, and I have built this network so that there are three clear communities, the red community, the blue community, and the green community, which are connected to each other. And so now I'm simulating the functional brain imaging data by the following procedure. So I am simulating an experiment where a stimulus is given in one of the brain areas. So, for instance, visual stimulus. So let's look at this picture again. So suppose one of the red nodes here is a visual cortex. So you give a stimulus there, and so then the brain activity moves into another brain area, and maybe it moves back to a third brain area, then maybe it comes back. So the connection can be used both ways. The signal may go from one brain area to another. And so when you are doing the experiment is registering the activity in different brain areas. And so your data may consist of a sequence of activated brain areas. So that's my assumption here. And so I'm simulating the data as follows. So I fix an index L, which is how long I am observing my network, okay? And so then I have a vector X, which is an indicator vector, which is telling me which brain areas are active. So I start with zeros in each position. So at the beginning, I have seen no activity at all. So then I start the experiment, and I see that one of the brain areas, which I choose random here, is activated. So I put random activity in the I0th position of that vector. So I'm adding a non-negative but random number in the I0th element. And so then I start moving in this network, and I'm doing this simulation so that the movement from brain region or vertex to vertex is random. So if you are, let's say, in one of the red vertices, you have three possibilities here. You can go left, you can go diagonally, or you can go up. And so which way you are doing the random walk is chosen randomly. So each movement that is possible have the same probability. So I'm moving randomly from node to node. So this simulates how the signal could go in brain. So we don't know where the signal goes, but we know that only those brain areas which are connected can be activated. And so when I'm moving to another node, let's call it IT+1, then I'm activating that brain area, and the activation is marked by adding a random contribution to the corresponding component. So when I make an experiment, my experiment outcome is going to be a random vector where I have non-zero entries in all those nodes which have been visited through this random walk. So this is the idea. So I don't care about so much about what the value is that I have in a given entry. The only thing that I care about is whether it's positive or not. So my data consists of these non-negative random numbers, and the non-negative random numbers are in positions corresponding to brain areas that have been visited during my experiment. And so now, how does my data look like? So here is one experiment. So my experiment started in one of those nodes. I'm not sure which one it was. And then I was performing a random walk around these nodes. So here white means high value, black means low value, and empty means that there was zero. So these empty nodes are zeros, and the non-zero entries are marked with a color, and the intensity of the color is telling you, or the grayscale of the color tells you what random number you have. So here this white means that there was a high random number connected with this node, and the black means that these nodes were visited maybe only once or a few times anyway. So the random number that they obtained through this process is low. Here is another experiment I started at some point, and then I just let my random walk move, and it moves in that community. Another experiment where I picked a non-connected node, so the random walk didn't go anywhere, and only that brain region was activated. Okay, so these are my data. So you can think that I have performed several controlled experiments with brain starting the stimulus in one of the brain regions, and then I have followed which brain areas were activated as a consequence. And so now my question is, based on this data, can I recognize which nodes are connected to each other? Meaning, can I identify the communities of the nodes? And so what I do, I collect these random vectors in my data matrix X, and then I make a non-negative matrix factorization. And here I, for the sake of the argument, I chose the rank to be 3. Of course, I have 3 communities, so this was of course a little bit of cheating, because I should have, I don't know that there are 3 communities, but so here I'm showing you the result when I happen to take the right number of communities. So I choose my rank of the matrix factorization to be 3. I will tell what happens if I don't do that. So my K is 3, and so then I calculate the non-negative matrix factorization, and then I'm plotting the feature vectors. So the feature vectors are these 3 images on the right here. And if you compare my feature vectors with the true communities, the red community, the green community, and the blue community, you see that they completely match with the communities. So this tells me that non-negative matrix factorization has the capability of identifying the connectivity structure of a network. So this is good news. So if this were a real brain activity application, this would tell me that my NM non-negative matrix factorization is capable of identifying the connectivity map of brain based on this type of controlled experiment where I see from which brain region to which brain region the activity is moving during the experiment. Now, I said that I fortunately picked k equals 3. So I have tested this algorithm also with other k values, and if I take k less than 3, what I typically saw is that these 3 communities, they are somehow connected. So part of, let's say, the green community is lumped together with the red community. If on the other hand I take more than 3 brain regions, there will be some, typically in the feature vectors, there will be some singletons which correspond to these non-connected nodes. So pretty much when I'm looking the results with different Ks, I see that there is a pattern, and the pattern is sort of favoring the existing structure. So this of course is the most optimal result where I happen to pick the right K. 3 communities K equals 3. But so the take-home message here is that the non-negative matrix factorization is indeed capable of identifying the connectivity map of your network. So this was good news, and so shows the feature of this non-negative matrix factorization, that it somehow gives you a summary of the data that you're looking at. And in this case, the summary is exactly what you're trying to find out, the connectivity map.
Excuse me, I have a question. Can you hear me?
Yes, I hear you.
Okay. So in those kind of experiments, as a data scientist, what do you receive as a data set? The underlying graph of the brain?
So what was the data set you said?
Yeah.
Well, the data set would be the activation map. So the activation would be these random vectors where you are observing where the activity moves. So these are the data vectors in graphical form. So each one of these vectors is an outcome of an experiment. So let's look at this data vector, for instance. I started at one node, and then I make a random walk. So the random walk was walking between these 3 nodes. So when you walk randomly, you don't know where the node is the walker is going. So I am in this blue community here, but for some reason the random walk just went back and forth between these 3 nodes. So this is how the data looks like, and I think I had 350 different samples of this stuff. Does that answer your question?
Yeah, okay. So the goal is to sketch, let's say, the underlying graph of the brain network.
Yeah, that's right.
Okay,
Yeah.
thanks. And another question, what would have happened if you would have set k equals to, I don't know, 2? Would some community overlap, or it just discovered 2 instead of 3 communities, or we cannot say in advance?
Yeah, well, if you make k less than 3, then those communities will overlap in your feature vectors. Yes.
Okay, thanks.
Yeah, that's what's happening. So yes. So you get overlapping communities if you make your k too small. But so we don't know what k is, but in this case I'm kind of cheating because I know what k is. So this is the sort of the optimal result, the best possible result in that sense. Yeah, thanks for the question, and I hope this clarifies.
Thank you. Yes.
Great. Okay, so I show you another example, which is one of the reasons why this non-negative matrix factorization became so popular, and this is related to text mining. So suppose you have a library or a corpus of texts, and you want to know what's in that text corpus, or you want to classify the texts in different categories. So you would like to have as we did in this previous example, you would like to have a quick summary of what this library is about. So what is a library and how you treat texts? So we are not going systematically through the text mining applications in this course, but I'm giving you the idea. So you are forming for each, let's say, think about the library where you have, let's say, books and articles and journals or whatnot. You, for each entry in your library, for each book or for each document, you form something which is a term document matrix. So you decide for a list of words that you are looking at. It may be a huge list of words, or it may be a small list of words. Depends on you of what you are interested in. But let's say typically you take a dictionary of 30,000 words. Now you go and count each word in each one of these documents, and so this can be done automatically nowadays. So nobody's going to count the words by hand, obviously. So you can count the words, and then you form a matrix so that each column corresponds to one of the documents, and each row corresponds to one of the words in the dictionary. So AIJ, which is called the term document matrix, the ijth element is the number of occurrences of the word I in document J. Okay, so this is how you form the term document matrix. So if you have let's say 300 books and 1,000 words that you are interested in, this matrix is 1,000 by 300. Okay, so this is what term document matrix looks like, and you can generate these automatically, and also if you want to test algorithms, you find also calculated term document matrices, and there are other word processing features that are often included, which I'm not going to discuss too much here. So this is enough for our purposes for now. And so then you can think that each unit vector, canonical unit vector, is corresponding to one word. So for instance, in my examples, 1000000 corresponds to the word plant if in my dictionary the word plant is in the first position. The word 2 could be, so 0100 could be baseball, it could be soil, it could be passport. So here I have some random words. And so I'm trying just to make you see that each canonical vector, basis vector, corresponds to one single word. And so when you take a document, your document is a combination of different words. So you get vectors where you have in each position the number of occurrences of that word in that document. So if you have a book of horticulture, for instance, then the first component in that document is going to be large because the word plant is appearing often in that document, whereas a book of horticulture has certainly almost certainly no mention of baseball. So the second component is going to be 0. So in this way, you can think that these vectors are somehow similar to my brain activity vectors. So you are just counting the occurrences of how many times a word is appearing. You may also divide each document by the number of entries in that document so that long documents and short documents don't look different. So you can scale your vectors so that the sum of the components is equal to 1. This is not necessary, it's sometimes done, and there are other weighting techniques that I'm not going to discuss too much, but so the idea is that to uniformize your dictionary so that a book of 1,000 pages doesn't look dramatically different from an article of 30 pages. So you can divide by the total number of words so that you have scaled vectors. Now, if you look at if you do this scaling, so here is a hypothetical vector with coefficient 0.6 and 0.4. So this would be a silly document which has only 2 words. So that document would be such that the word plant is occupying 6 out of 10 occurrences. Of course, what would that document be? This is just a hypothetical, but I'm just wanting you to see what I mean by this. And then the word soil was number 3. So in this document, there are 6 out of 10 appearances of the word plant and 4 out of 10 appearances of the word soil. So you would conclude that this article, if you see this vector and you know what these words are, you would conclude that this document is about horticulture or gardening, because it obviously has a lot of appearances of those important words. Okay, so now we have the picture. So now suppose I have a term document matrix, and I want to figure out what's in that corpus. So what are the documents talking about? So this is my question. So what I did here, I took an example which you can download also from internet. This is the NIPS meeting, which is a Society of Artificial Intelligence and Neural Information. So this neural information processing systems is an old word. They usually refer to this conference now as artificial intelligence meeting. And so I have in this term document matrix the proceedings from 1987 to 2015. So how many documents do we have? We have 5,812 documents. How many words do we have? 11,463 words. So this matrix I just downloaded because this was calculated, and so I wanted to see if I can figure out what this corpus is about. So can I figure out that this is really library of let's say artificial intelligence and machine learning? So this is my question. So the dictionary is so-called induced dictionary. So that means that all the words that appear in any one of those documents is included automatically into the dictionary. And so they didn't do what is known as stemming. So the word compute and computing, they often are, if you do so-called stemming, you take the ending away, so that compute and computing would be the same word. But in this dictionary, this was not done. And so compute and computing, for instance, are two different words, although they are clearly closely related to each other. So now my question is, if I have no idea what this database is about, does NMF give me a reliable summary? And so I'm going to run my NMF with few feature vectors. So I'm doing exactly the low rank approximation of my data. And I took my k equal to 6. And so then I run the NMF. It takes less than a minute, I believe. I don't remember the runtime, but so this NMF, the multiplicative updating algorithm is really fast, and so you don't have to wait for long. When I do that, I get 6 feature vectors. Each feature vector is having 11,463 components. And so I'm looking at the first feature vectors, and here I have sorted the components into the decreasing order, so that the largest component equals 1, and then the other components are scaled respectively. So I'm dividing each feature vector by its L infinity norm. So the largest component after scaling is 1, and of course each column is sorted differently here. So we have to understand that these are differently sorted columns. So there is a word in the first column which is most frequent, and then the second frequent word is has a frequency of 0.65 compared to the most frequent word, and the third frequent word is 0.58 compared to the most frequent word, etc. So I'm just looking at the numbers, how frequently these words are appearing, and I see that there is clearly always a very prominently outstanding word, and then some auxiliary words which are helping me to understand what the dictionary is going to be about. So when I do this sorting, of course I want to know what is the word that has the highest frequency, and what is the word that has the second highest frequency in each one of these feature vectors. And so here is what they are. So in my first feature vector, the word that had highest frequency was network. The second highest word was neural, then input, networks, time. So notice network and networks is twice. So normally you would stem your words that network and networks are the same word, but in this databases this was not done. Okay, so I see that this first feature vector obviously is talking about neural networks, I would say. The words that I see here are typically words that are describing neural network articles. The second feature vector is learning, state, function, policy, algorithm. So this is probably some sort of machine learning category. And then I have data, image, training features. So maybe this represents articles which are talking about images because the image is so high. So maybe this is where here the data consists of images and you are doing some sort of training. I don't know exactly what it is. Images is here again. So category 3 seems to be talking about images. Category 4 is clearly something which has to do with Bayesian methodology because there's the words distribution, Bayesian, Gaussian, posterior, prior. So these are words that are typically characteristic to an article that is talking about Bayesian methods in data science. So W4 is certainly something that has to do with data, with Bayesian methods. Then there is model, models, time, figure, state. So this is something which has to do with modeling. And then we have something which looks like a linear algebra class because there are matrix, function, theorem, problem. So this is probably something that refers to strongly mathematical contribution. So looking at this, you get pretty quickly an idea what this corpus was about. Now let's go and see this category 4. So I'm convinced that category 4 has to do with Bayesian methods, and I have 6 categories. So could it be that about 1/6 of these articles are Bayesian? So as I showed you earlier, I had this data set where I had 3s and 7s, and the number, how many times these feature vectors were looking like 3s and 7 told me also how often a data vector was a 3 or 7. So now my question is, I have chosen a little bit arbitrarily 6 to be my K, but it looks like only one of those vectors is somehow Bayesian, so this W4. So maybe there is about 1/6 of these papers are Bayesian. Let's see if I can make any sense of that. So so what I'm doing, I'm doing a query matching, and query matching means that you take a word, which this time I choose my word to be Bayesian because I'm interested whether there are Bayesian articles which are talking about Bayesian methods. And so what I'm doing now, I'm doing the following. I take my, let me see, L is a scaling. And so I'm scaling each one of those documents by the L infinity. So I forgot to say that this is the infinity norm. So I'm taking my data vectors and I'm scaling them so that they are normalized. So then I take my query word, which is Q, and it's just consisting of one word. So how does this vector Q look like? It is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, and the 1 is corresponding to the row where my word Bayesian is. Okay, so if I take the inner product of Q transpose times my data, so this inner product is 0 if the word does not have the word Bayesian, because you think so the inner product of Q with that column of X is 0 if that column of X is a document that does not contain the word Bayesian, because when you calculate the inner product, the only contribution comes from that particular row. So this process, this M here, is simply a word count, how many times the word Bayesian appears in each one of those documents. So I'm picking the row that corresponds to the word Bayesian. I'm looking at the frequency of how many times in each document the word Bayesian is appearing. Okay, so I hope this is clear. So I'm just slicing my data through, and I'm looking at the row corresponding to the word Bayesian. And so then I'm asking, so this is something that is done often in text mining. I'm asking in how many I'm trying to find a percentage of papers that that contain the word Bayesian, and so I don't say that this MJ has to be 0. I'm saying that its frequency should be at least threshold tau. So tau is saying, let's say that if you say tau is 0.01, then you are looking for papers that has the word Bayesian at least so many times that the frequency of the word Bayesian is 1%. If I take tau to be 0.001, then I'm looking for papers where the word Bayesian appears with frequency 0.1%, etc. So this tau is sort of a cutoff frequency. If I put tau equal to 0, then I'm looking for papers that at least once have the word Bayesian. And so then I'm plotting this number here, and I see that the plot looks like this. So here is the threshold value tau, and here is the percentage-wise appearance of the word Bayesian. So interestingly, if I put tau really large, like equal to 1, of course, there is no paper that only contains one single word Bayesian. So you should expect that this percentage is 0. When my tau is close to 0, then I'm asking how many papers have the word Bayesian at least, let's say, once. And it looks like in this corpus, about 1/3 of papers, 1/3 of papers is saying the word Bayesian at least once, because I get 33%, more or less, 32.5 maybe. But so this analysis seems to tell me that about 1/3 of the papers at least once mentions the word Bayesian. Of course, that doesn't mean that the paper is about Bayesian methods, because you could have a paper saying, unlike in Bayesian methods, here we do something else. So that is a phrase that uses the word Bayesian without the paper being Bayesian. Okay. So you can, if you make an educated guess, saying that about 1/2 of the papers which are saying the word Bayesian are not Bayesian, and 1/2 of the papers which say the word Bayesian are Bayesian. So then you would end up to saying that, well, about 1/6 of the papers are about Bayesian methods. This is, of course, a guess. But so looking at this picture and looking at this table, I would come to the conclusion that, first of all, 1/3 of the papers are using the word Bayesian. That's my analysis. And since only one feature vector is clearly related to Bayesian methods, I would say that 1/2 of the papers which are mentioned in the word Bayesian are really using Bayesian methods. So this is a way how you can analyze a corpus of data using non-negative matrix factorization and other clever ideas, like I use query matching here. So this process here that I did here. So this is called query matching. So you're checking how well your documents are matching with your query, and my query in this case was the word Bayesian. And so when I have this term document matrix, the word Bayesian can be translated into a vector. And this vector is simply a vector which has 1 in one place and 0 in others. I could do a refined search, and I would use a query where I have 2 words, let's say Bayesian and posterior, for instance. So then I would have Q as a vector which is having 1/2 in the row that corresponds to the word Bayesian and 1/2 in the row that corresponds to the word posterior. And so then doing the same analysis, I would be able to analyze how many papers are, containing with certain threshold that is sort of an indicator of the significance of that word, the appearance of that word. So how many of these papers are containing both the word Bayesian and posterior? And so that would be a refined analysis. But so this was just to give you an idea what you can do with non-negative matrix factorization. So from now on, the analysis is depending on the user's creativity. So this is a nice tool to take a look at the contents of a library or a corpus. So this application, I believe, was one of the main reasons why this non-negative matrix factorization became so tremendously popular. Because in that Nature paper that I was referring to, the authors they proposed this idea of looking at text data, and so the community picked it up quickly and understood that this is a nice tool to analyze text corpus. I believe this is my last slide on non-negative matrix factorization. So let me see. We are. So maybe I start before we make a break. I start the next set of slides. Let me change the set of slides. Okay, here we go. Just a moment. What did I do? Wait. I wonder if you see my screen now. Do you?
Not yet.
Not yet.
Not yet. Okay, so I'll try again. So let me. For some reason, it doesn't let me to share the screen. I seem to have a technical problem here, which is okay. So here we go. Now it works.
Yes.
All right, good. Okay, so this is the next theme in this series. So SOM, self-organizing maps, and so they are also, the self-organizing maps are also referred sometimes to Kohonen maps, and this is because of the inventor Teuvo Kohonen, who was one of the promoter of neural network ideas in early on, and so he published in 1982 this rather influential paper in biological cybernetics, which is called Self-Organized Formation of Topologically Correct Feature Maps. And so Teuvo Kohonen was, he still is a professor at Helsinki University of Technology, which is now called Aalto University. This is where I previously worked, and so in the 80s he was having his very influential seminars when he was sort of introducing and developing these ideas, and so they were, as I said, influential and popular seminars, and so I want to explain a little bit the origins of this idea, because some of the terminology that he used early on has been inherited by the community, and so it's interesting to understand where these ideas come from. So Kohonen was inspired by so-called brain maps. So at least in the 80s, there was this idea of I think it's called Hebbian learning, where the idea is that the neurons that are wired together, they perform the same sort of task in brain. So there is this phrase saying "wired together, fired together," which is sort of the mantra of Hebbian learning. And so the idea is that when we are children, our brain is highly connected. So we have way too many synapses when we are born, And so then the learning process means that the brain organizes itself so that it prunes out certain connections and reinforces other connections, so that when we are learning and we are processing data, the brain is organized in such a way that neurons which remain wired together, they are sort of performing the same task. And so the topographic location is, I mean, you have connected brain regions, so you may have areas which are far away from each other, but the important thing is that these areas are connected so that they are sort of performing the same kind of task. And so we can think that there are two kinds of concepts here. There is the concept of topology, and there's the concept of geometry. Geometry means that two stimuli are similar, so the data vectors are similar, then they are geometrically close. While two brain regions which are connected, but they may be geometrically far away, they are topologically similar. So that's somehow the idea here. So let me try to explain it a little bit better with this picture. So here you can think that this is a central sulcus of the brain, and so they are these gyri. And now in the central sulcus, you have on one side you have the motor cortex, and on the other side you have the sensory cortex. And so motor cortex and sensory cortex, they are having very different functions. So one is controlling the movement, and the other one is sensing. So although they are geographically close to each other, or geometrically close to each other in the brain, they are performing different tasks. And the fact that they are performing different tasks is manifested by the fact that they are not directly interconnected. So these two brain areas, they are connected, but not by the vicinity of these brain regions. It's the topological organization of the brain. So here is a picture of brain where you have all these this is a diffusion tensor imaging picture of the brain, which is a connectivity map of the brain. And so you see that there are these filaments going from one side to another. And so you can argue that the gray matter in one part and the gray matter in the other part, they are somehow performing similar tasks because these two gray matter areas are connected by these white matter filaments here. So physically nearby regions may be topologically distant because they are not necessarily interconnected by these brain connections. And the topological distance may imply functional diversity. So for instance, sensory cortex and motor cortex, they are not immediate topological neighbors. And so therefore, you can argue that these two areas are performing different tasks. And you may have topological proximity through brain connectivity. So by this I mean that you may have two different areas which are geometrically distant, but they are topologically close because they're connected. And so in this self-organizing map context, the geometric proximity is understood as processing similar stimuli. So this is about the similarity of the stimuli, not the sort of the geometrical nearness of the areas. So this is not that important from the point of view of self-organizing maps. I just wanted to give you a little bit of the background because sometimes people are using words like neurons in the connection of self-organizing maps, and so you may wonder where this word neuron comes from. So the origin is because this is sort of brain-inspired algorithm. So that's the background. So so SOM, what does it try to do? SOM is trying to, as the name said, it is trying to organize the data. And it is trying to organize in such a way that it is easy for us to interpret the data. So we are in a high-dimensional data space, and each dimension in the data space corresponds to an attribute. And for us, it's very hard to imagine the organization of the data in a high-dimensional space. So we are capable of understanding the organization, the topological organization of things in 2 dimensions. Already in 3 dimensions, we start or may have some problems. So, for instance, when you hear interviews of brain surgeons, for instance, they often say that the most important sort of skill that they have a 3-dimensional sense of things, because you have to navigate very carefully in the brain so that you don't touch areas that you should not touch when you're operating. And so already the 3-dimensional understanding of 3-dimensional structures and connectivities is rather challenging for us. If you go to 4 or higher dimensions, you certainly start to have great difficulties, because we don't really we don't know how 4-dimensional space looks like. So just to give you an idea, so if you look at the famous Poincaré hypothesis, it's about 3-dimensional manifolds in basically 4-dimensional spaces, and it was considered to be one of the hardest problems in mathematics, telling you how difficult it is for us to understand higher dimensions. So we understand well 2 dimensions. 3 dimensions already starts to have some challenges, and 4 and higher, our understanding is not so good. So self-organizing map is trying to find low-dimensional structures in data, and let's say topological structures. So SOM is trying to figure out which data points are close to each other in high-dimensional space and represent the data in such a way that we can understand it. That is typically 1 or 2-dimensional projections of it. So that's the the ultimate goal of SOM, and it also gives you some idea how you can classify your data. So there are classification algorithms that are sort of following the SOM idea, which I'm not going to talk too much. I may mention something about that later. Okay, so here is an example. So this is one of the canonical examples that the people in Kohonen's information laboratory were using. So they were looking at a quality of life data. So the data is collected in different countries, and the attributes are referring to in general what we consider to constitute the quality of life. So gross national product, level of healthcare, education, level of corruption, freedom of press, that sort of things. They were all quantified. And so now you have these vectors with lots of attributes. So each country has one vector. Okay, so this is the quality of life data, and this is an old project, and they continue collecting this data. So it is interesting to see how it changes over the years. Now you can think that 2 neighboring countries, although they are geometrically close to each other, they may not have the same quality of life data. So it is easy to imagine 2 neighboring countries which are very different from the point of view of quality of life. On the other hand, you have countries which have similar tradition and similar history. So let's take, for instance, New Zealand and Canada. They are far away from each other. But if you look at the sort of the history of those countries, you understand that they may be close to each other. They have the same language. They are countries whose political system originates from the same source, etc. And the people who went there, they are sort of representing the same original culture. So you may think that these countries have similar quality of life data, although they are far away from each other. And so this SOM is trying to organize the countries in such a way that you see which countries are close to each other topologically, and then you can have a sort of a visual map of how the world looks like from the point of view of quality of life. So here is an example. So this is an old outcome which you can find in just by googling the SOM. So let's look at the word map, and let's look at this two-dimensional representation. So this two-dimensional representation below is the topological organization of the world. So you can see, for instance, let's look at the countries that I mentioned. So here is Canada, and here's New Zealand. So you find somewhere New Zealand and Canada, and I checked this, but now I got, yeah, here's Canada and USA. So it's on the very left, Canada and USA, and below Canada and USA you see New Zealand. So you see that Canada, USA, and New Zealand are sort of close to each other, and Australia is also in the same region. There's also Israel. So you can argue that from the point of view of the quality of life data, those countries are close to each other. Although in the world map, where they have now colored using the color scheme that is inherited from this two-dimensional map, they have the same kind of color. So you can read from this map which countries historically, let's say, or from the point of view of socio-economic organization, are similar. And so this is the self-organization. So we take the data and we let the data organize itself in such a way that you have a two-dimensional map which is telling you who is close to who. So that's the basic idea of self-organizing maps. And I believe that if we want to make a break, this would be a good place, because then I go to details, the mathematical details, and I'm starting to explain what this algorithm looks like. So let's make, as usual, a break of about 10 minutes. So if we continue at 10 minutes past the hour, so 4:10, I'm continuing from here. So 13 minutes break, so you can stretch your legs and have a coffee. Okay.
Okay, thank you.
Thank you.
Thank you.
Thank you.
Thank you, Professor.
Thanks. Okay, I think it's it's time to continue. So welcome everybody back to the second part of this class. So I gave you an overview what the sort of the origins of self-organizing maps is, and a little bit of what sort of goals do we have. So we want to have a low dimensional representation of high dimensional data. So when I say it that way, it does sound pretty much similar to what, sorry, I'm just, yeah, okay. So it sounds pretty much similar to what we did in PCA. So in PCA too, we were trying to reduce the data to a low dimensional subspace. Now, what is the difference here? The difference is that the data is not always organized linearly. So if you have a data in high dimensional space, which is organized around a plane, let's say, the PCA analysis gives you the vectors that are spanning the plane, and you get a nice representation of your data. Now, in general, data need not to be organized in a plane. It may be a question just to choose wrong coordinates. So think about your data, which is organized in a plane, and then you use spherical coordinates in let's say 3 dimensions. So then in the spherical coordinate data, the data is no longer a plane, it is something else. And but we don't know what coordinate system would take us there. So in general, we could have the situation as in this picture here in the center of the page, that you have the data which are represented by the green squares here, and so you see that there is a curve that is passing neatly through these data points, but and so following this curve will organize your data into a linear order, more or less. And so that's what you would like to have. So you see that if you follow this curve, you have a natural organization of your data. Whereas if I take a projection direction, so in this case, probably the PCA direction, so the direction of maximum spread would be more or less a line from M1 to M2, MK. And if I take a projection of my data to that direction, you see that there's a huge overlap. So the data is jumbled up. It is not organized as it would be organized into a linear scale by using this curve. So the question is, we want to find this curve. And this is related to a topic in data science, which is called manifold learning. Manifold learning means exactly that you have the data in high dimensional space and you're trying to find a manifold, which I at least visualize to myself like a surface, a smooth surface, a lower dimensional object which is living in the high dimensional space, and so that this surface or this manifold is sort of capturing the distribution of the data. And so SOM seeks to approximate this low dimensional manifold by prototypes. So instead of trying to find a continuous curve, we are trying to find prototypes which are concatenated to each other. And so we are trying to place those prototypes into the data set. And so then following the way that the prototypes are concatenated, you get an organization of your data. You have an organization of your maps. And so this is the self-organization. Okay, so the goal is, like in this example, M1, M2, etc., MK, they would be the prototypes. And so there is a natural ordering of those prototypes, which is indicated in this straight line here, Q1, Q2, etc., QK. So you can think that each prototype MJ is related to a lattice point QJ in this linear lattice. And so then if I just pull down the data from the data space to this linear lattice by saying that each data point is mapped to the lattice point which is closest to that data point, then I have an organization of my data. So that's the idea. Now, we can formally think that we have a d-dimensional lattice where d is typically 1 or 2. So we have a two-dimensional lattice or one-dimensional lattice. Then we have a mapping from this lattice to the prototypes. So each lattice point is mapped to a prototype, and this prototype is living in the high dimensional space where the data is. And so then you have one-to-one correspondence between the lattice points and the prototypes, and then these prototypes are telling you where the data is in the space and how it should be treated in the low dimensional lattice. So you take the nearest prototype, and then you are just pulling the data down to the lattice. So that's the idea. So because of the origin of the self-organizing map as being inspired by the brain organization, these QLs are sometimes called neurons. I'm not using that word because I think it's confusing. We are not doing anything with brain or neurons, but if you see the word neuron in this context, you now know why this is so. The Qs, well, sometimes even these M's are called neurons for some reason because they are one-to-one. So but I don't like that word because it confuses me only. So I'm calling Qs lattice points, and I'm calling M prototypes. And so we can say that MJ and MK, which are two prototypes, they are neighbors if QJ and QK are neighbors in the lattice. So this is the topology. So the topology means that you're telling who is whose neighbor, and you are reading from the lattice, the neighborhood structure, and then your prototypes are inheriting the same prototype structure, the topological structure. And so then you say that your prototypes are neighbors if and only if the lattice points are neighbors. So this is how the topology enters. And so then the geometry is how close, you know, a data point is to any one of those prototypes. Okay, so now we have the concept of topology. And so here is an outline, a verbal outline, and then we do it in mathematical terms. So you initialize your self-organizing map by just throwing a handful of these prototypes into the data space. Sometimes they are called weight vectors. Yeah, this is a word that you sometimes see in this context. So we take the prototypes ML and we throw them typically in a random fashion into the data space. So this is somehow mimicking the infant brain, which has lots of connections, and so you have no structure yet there. Now we start to represent the data by selecting a stream of data vectors. So either I'm going in a random order through my data set, or if I'm looking at the dynamic system, my system is generating the data vectors. So xt is the data vector that is presented at time t. So we are presenting the data one data vector at a time to our system. And so when the data vectors are presented, the prototypes are moved in this data space. And there is a set of rules how you move these data vectors, these prototypes in the data space. So you basically take the prototype which is closest to the presented data, and you move that prototype towards the data. So you take a step here and updating one of the prototypes, and you move it towards the data so that it better approximates the data. Now you take into account the topology. So you can think that these prototypes are connected to each other by an elastic net. And when you are pulling one of the prototypes, then the prototypes in this elastic net, which are close to that prototype, they are moving along. And prototypes which are farther away from that nearest prototype, they are moving less. So you can think really that this is like an elastic network that you are throwing into the data space, and then you start moving the nodes of that network. And when one data point is moved, then those prototype is moved, then those prototypes which are connected to it, they move along. And so little by little, you are stretching this network so that it approximates your data in the data space. So this is a verbal description, and so then we can start looking at the mathematics. So here is how you do this in practice. So suppose xt is the data vector that you present at time t. Okay, xt refers to the data that you show at time t. First, you identify what is known as the best matching unit, BMU. It is the prototype that is nearest to the data. So remember, we have finite number of the prototypes, and so it is easy to check which one of the prototypes is closest to the newly introduced data, xt, and that's called the best matching unit. So here is the formal definition. I'm going to denote by MJT, the best matching unit. And so this MJT is the prototype that minimizes the distance of all prototypes to the current data. So you are looking at, you're calculating all the distances. There should be, never mind. So this is correct, but maybe for consistency, I shouldn't have this second power here. So it looks a little bit strange, but anyway, so yeah, these two should be away. So I'm calculating the distance of each prototype from the current data, and I'm picking the one which minimizes the distance. So that's the best matching unit. And so then I'm updating my best matching unit. What I'm doing, I'm moving my best matching unit towards the data. And here is how I move it. So I take the vector that is pointing from my prototype to the data point. So that's in the data space, a vector. I'm scaling that vector by a factor alpha, which is less than 1. And then I'm replacing my current position of the prototype by the new position of the prototype, where I have moved the prototype towards the data by a step which is proportional to this alpha, and it is proportional to the vector between the data and the best matching unit. And so this alpha here is called the learning rate. Now, suppose I put alpha equal to 1, so what happens? Then I would move my prototype on top of the recently introduced data. So this is not something that I want to do. But if I would exaggerate and put alpha equals to 1, then my prototype would overlap with the data point. But in general, I'm just moving it towards the data. So that's the idea. So this is the basic move here. Now, we are doing a little bit more. So we are postulating that two prototypes are near each other topologically if the lattice points are near to each other in this lattice Q. And to measure the nearness of the lattice points, you can use whatever metric you want. I'm using here Euclidean metric. So I'm taking the lattice points in this low dimensional space, so 1-dimensional or 2-dimensional space. And then I'm saying that two lattice points are topologically close to each other if their Euclidean distance in this Q space is small. The prototypes may be far away from each other if you wish. So we are not measuring the distance in the data space or in the physical space. We are measuring the distance in this lattice, and the lattice is unchanged. So the lattice does not change during this process. And so, as I said, the typical distance between the lattice point is the Euclidean distance. We have dij, and so then we have a distance matrix. And this distance matrix is calculated only once. This is a constant matrix, so it doesn't change during the process. Okay, so this is an important feature. So then we define something which is called the neighborhood matrix. And the neighborhood matrix is measuring the coupling strength. So I'm using the Gaussian neighborhood matrix, which is exponential of -1/2 gamma squared times the distance between two nodes, two lattice points. So this gamma here is a coupling constant. It is telling how strongly nearby neighbors are coupled. So if gamma is large, then my Gaussian distribution, which I'm using here, is wide. And so that means that lattice points which are physically distant from each other in the lattice, they are coupled because this h is a number which is close to 1. Whereas if I make this gamma small, then this exponential function is decreasing very rapidly. And so that means that lattice points which are far away from the current lattice point, they are unaffected because the neighborhood matrix is giving a small index. So the larger the index hij is, the stronger coupled to lattice points are. So this hij is simply measuring the coupling strength between my lattice points. So that's the interpretation, and the definition is very straightforward. And so you will see how I'm going to use this. So when we go to the algorithm. So first I introduce these concepts, and then we start, systematically move the lattice point. And so here is the idea. Suppose you have identified the best matching unit, okay? So you say that MJT is the best matching unit. Now you take the coupling matrix H, and remember this coupling matrix is large if the mesh points, the lattice points are close to each other, and it's small if they are far away from each other. And so then I'm moving the prototypes corresponding to any one of those lattice points according to how strong the coupling is. So I'm moving all these prototypes ML towards the newly introduced data point. But I'm not moving as much as I move the best matching unit, because I'm multiplying this learning rate alpha by a factor h, which is less than 1. So for the best matching unit, this h is 1. So I'm moving the best matching unit with the learning rate alpha. For prototypes that correspond to lattice points which are far away from the best matching unit, this h is almost 0. And so those prototypes are not moved at all, or are moved very, very little. And so this is the elasticity idea of the network. So when two prototypes are close to each other topologically, those prototypes are moved together, while if the prototypes are far away from each other topologically, the moving of the best matching unit doesn't affect the other prototypes. So for the best matching unit, this coupling constant is 1. And the closer the lattice point QL is to the best matching unit lattice point, the stronger the prototype vector is updated. And prototypes with distant lattice coordinates remain essentially intact. So this is what I try to explain with my my explanation. And so the connection between the prototypes is thought of as some sort of elastic strings. So here is a picture. I'm trying to make this as geometric as possible. So here is a simple lattice, a rectangular lattice. So I have lattice point Q1, Q2, Q3, etc., all the way to Qk. So I have k lattice points, and you see the neighborhood structure here. So I'm assuming that, so you can think that there is some sort of elastic membrane or elastic mesh between, which is connecting these lattice points. And so then here I have the prototypes. And so the prototypes inherit the same topology as the lattice has. So if I in this picture have two lattice points connected, then the prototypes are connected in the data space. So this net here on the right is representing the prototypes, and so they have this topological connectivity with each other. So now the new data point xt was introduced, and so I'm identifying the closest prototype, which is the best matching unit, and I call this MJT. So this green point here is the best matching unit. And so what I'm doing now, I'm moving this green point towards my xt, and that is pulling together the nearby prototypes, while a prototype which is far away is left almost intact because the topological distance is large. So that's the idea. And so here is the algorithm. We have a, let me see what I have to say. Okay, so I'll show you this picture first. So this is maybe more intuitive. So here are my prototypes. the black dots are prototypes, and this green square here is the data that I'm presenting to my prototypes. I identify the best matching unit, and then I'm moving all these nodes towards X, and the movement is the stronger, the closer the prototype is to the best matching unit. And so here is a picture when gamma is large, or if gamma is small. So when gamma is large, that means that my prototypes are strongly coupled. So that means that when I'm pulling my best matching units toward XT, it pulls the whole net with it. Okay, so this is for gamma large. So when the coupling constant is large, then I start to decrease the coupling constant, and you see that the smaller gamma I take, the less the moving of the best matching unit is affecting the other nodes. So here is some sort of intermediate value for the coupling constant, and you see that some of the prototypes which are here far away from the best matching unit, they are not affected at all. And when I make gamma really small, so then I'm sort of reducing the coupling between my prototypes, and essentially only the best matching unit that is near its neighbors are slightly affected by the updating. So depending on the coupling constant, I can control whether my prototypes are moving together or if they are just moving one by one. Okay, so this is the basic idea. So let's go to look at the algorithm. So first of all, I'm using a dynamic learning rate. So remember, alpha is the learning rate. It tells you how fast or how much I'm moving the best matching unit towards the current data vector. And so I'm taking this alpha to be a time-dependent variable, so that I start with the value alpha 1, which is the original initial learning rate. And then I'm letting my learning rate to decrease to some value. Oh, let me see. No, I'm starting with alpha 0. Yes, so when t is 0, so alpha 0 is larger than alpha 1. So at the beginning of the learning process, my learning rate is alpha 0. And at the end of the learning process, my learning rate is alpha 1. And so here I'm decreasing linearly the learning rate. So I'm starting with a large value of alpha, then I'm going down, and little by little I'm slowing down the learning rate. And T0 is the duration of the learning phase. So after the learning phase, this alpha takes the value constant alpha 1, and so I have a constant learning rate. But at the beginning, I want to make the learning a little bit faster, and so therefore I'm using a larger learning rate. What about the coupling? The same thing with the coupling. So at the beginning, I'm using a large coupling, gamma 1. So I'm saying, gamma 0. So at the beginning, I'm saying that all the nodes are connected. So when the best matching unit is moved, the whole group of prototypes is moved, and little by little I'm decreasing this gamma, so that at the end only the best matching unit and its immediate neighbors are moving. So there are two time-dependent constants. There's this learning rate, how much the nodes, the prototypes are moving, and gamma, which is telling how strongly connected the prototypes are. And so based on this idea, I'm using the updating by presenting one data at a time, moving the prototypes according to this scheme. So this is the idea. So at the beginning, I want to move all the prototypes when I present the data, so that I get my prototypes nearby where the data lives. And then once my prototypes have learned already something about the structure of the data, I start slowing down the learning. So I'm decreasing the learning rate, but also I'm making the prototypes more independent. So I'm decreasing the coupling between the prototypes. And so at the end, I'm just adjusting a few prototypes at a time, so that they are approximating better and better the data. So here is the algorithm in all its simplicity. So this is really how you do it. You fix k, the number of prototypes. You define a low dimensional lattice, which is typically a line or a rectangle. So you're defining these lattice points. Then you decide what is the maximum number of iterations, the learning process, the length of the learning process. And so Tmax is how many data points you're going to represent to your system. You initialize, you throw your prototypes, let's say a random cluster into the data space, and you set your counter equal to 0. And the current prototypes are denoted by ML0. So the 0 is the time t. For every t, you iterate as follows. You represent the data xt. So you show one data point. You find the best matching unit. So you look what prototype is closest to the data. So this is the definition of the best matching unit. Then you calculate the current learning rate and the coupling rate. And having those, you update all the prototypes according to this simple rule. You move your prototypes towards the data that is being presented, but so that the learning rate controls how much you move, and the coupling constant is also reducing the step according to how close your prototype is to the best matching unit. And then you increase the counter, you advance the counter by 1, and then you repeat. So it's extremely simple to implement. It takes really like few lines to implement, and it's amazing what this algorithm after all can do. So here are some parameter values that typically are recommended people who have thoroughly tested these algorithms. So the Tmax should be larger of, let's say, 500 times the number of prototypes. So if you have 10 by 10 prototypes, so you have 100 prototypes, so then your T should be at least 50,000. So that's the number of data that you are showing. At the learning phase, when things are moving, before you plateau your learning rate to the lower value alpha 1, when you are decreasing linearly the learning rate, you should take at least 1,000 steps. So the fast learning, the learning phase should be about 1,000 typically. What are the recommended values of the learning rates? At the beginning, you should use a large value, so 0.9 is a good guess. And when the learning phase is over, you have this adjusting phase. So alpha 1 could be 0.01. So your learning rate is decreasing from 0.9 to 0.01 typically. How about the coupling constant? Well, a typical recommendation is that at the beginning, your gamma, the width of the learning function, should be about 1/3 of the width of the lattice. So n is the width of the lattice. So if you have a 2-dimensional lattice, let's say 10 by 10, so then n would be 10. If you have a 1-dimensional lattice where n is, let's say, 100, then typically gamma would be, n would be 100. So you take the diameter of your lattice, and you say gamma is about 1/3 of the diameter of the lattice. And at the end, your gamma should be of the value 0.5. So that means that only the neighbors of the best matching unit are affected at the end. So these are good parameter values. And so then you just start implementing. So let's see how this works. So here is a simple 1-dimensional example. So my data is in this toy example. Data consists of points on a unit circle. And so I'm drawing the angle theta t from uniform distribution between 0 and 2 pi. So I'm representing to my SOM data points on a unit circle. And so what I want my SOM to do is to understand the geometrical organization of the data, so that the data is really appearing on a unit circle. So this is a one-dimensional manifold in 2-dimensional space, and I would like my system to learn the topology. That is, to understand that the data is organized on a unit circle. So if I look at one single data point is just a point in a plane, and it shows here and there on the unit circle. So I want my system to learn that the data is always represented on a unit circle. So that's the idea. I'm taking my k equal to 30, so k is the number of the prototypes, and I'm using one-dimensional lattice. Okay, and so I start by drawing the initial prototypes from a tiny little box near the origin. So I'm throwing them randomly, drawing the x and y coordinates from uniform distribution between 0 and 0.01. So there's a tiny little group of prototypes almost at the center of the circle. So that's what I'm starting with. I'm sorry. And so the lattice points here are L. So I have a one-dimensional lattice. So my Q1 is 1, my Q2 is 2, etc. So one-dimensional lattice, numbers from 1 to 30. Parameters are chosen as the recipe told me. And so now let's see how this works. I show you some snapshots of my SOM. So T is 1. I'm presenting the first data point, and my learning rate is 0.9. So you see that I start with my prototypes all in the center of the circle. And so here is the red square, which corresponds to the data that is presented. And so what happens is that all these prototypes start to move towards this data point. And so the best matching unit is moving most. It almost reaches the data point, and the prototypes which are connected to it according to the topology. I have indicated how the prototypes are connected topologically to each other. You see that this is like a some sort of chain that is pulling out, and one point is being pulled towards the data and the others are following. So T equals 2, I'm presenting this point of data, and you see that this chain is starting to unfold. T is 20, I already have the chain pretty much opened up so that the prototypes are in a linear order. T equals 50, we are still deep in the learning state, and you see how this prototype chain is opening up. T equals 100, and it starts T equals 500, it starts to take a little bit this circular shape already here. And so here I'm decreasing already the learning rate, and I'm decreasing the coupling constant. So this goes on, T equals 1000, this is the result, 2000, 4000. Now you see that my prototypes start to organize themselves to the low dimensional manifold where the data is.
And qualcosa di sopra ci sta, forse qualcosa di piccolo in mezzo a di lui. Forse ci sta qualcosa, ma no.
Okay, somebody has a microphone open. Is that a question for me or something else? Maybe not. Okay. So we continue. T equals 800, T equals 8,000, 12,000, and 15,000. And you see that when I go all the way to 15,000, which is the last iteration, so you see that my prototypes are neatly organized around this manifold where the data is. So I can argue that my system learned the manifold pretty neatly. So looking at this picture, there is no doubt that the data is sort of organized around a one-dimensional manifold here. And so now if I stop the learning process and keep these prototypes, so if data continues to come, I can always represent the data by saying which one of the prototypes is closest, and that tells me where, topologically speaking, the data appears. So this is a nice example of how this self-organizing map learns a low-dimensional manifold. And so you can imagine that if you are in higher dimensional space than 2 dimensions, where you can always look at things. So you can think that you are in 100-dimensional space, but your data is organized in a circle in that space. So it is very valuable that your prototypes are understanding the low-dimensional structure of the data. So this is a toy example. I show you another toy example. I'm taking 300 data vectors in 3-dimensional space, and I'm assuming that they are distributed near a hemisphere. And also to see how this organization can be visualized, I'm assuming that my data represent 3 different classes, which I'm printing with different colors. So I'm going to have blue data points, red data points, and green data points. Okay, and so I'm hoping that my self-organizing map, which now is a 2-dimensional network, is learning the distribution of the data on that hemisphere. So let me show the picture first. So here is the picture. So I have 3 types of data points. I have these green data points, blue data points, and red data points, and they are organized on a hemisphere. And so here you are looking at the final result. So the black dots here are the prototypes, and to make this visually compelling, I have connected the prototypes according to their topological vicinity. And so you see that this 2-dimensional network is capturing the data nicely. So I started here. So let's go back to the previous slide so that you see what I did here. So I chose 100 prototypes. So I took a 10 by 10 lattice, and I threw the original prototypes in a tiny little cube in the center of this sphere. My coordinates QL are in a 10 by 10 lattice. My learning rate and T are chosen according to the recipe that I told you, and the original learning rate is here, and the coupling constant at the beginning, at the end, are also chosen as I indicated. So notice here the diameter is of my lattice is more or less 10. Of course, if you measure the diameter diagonally, it would be more than this. But I took the let's say L infinity diameter of the lattice, and so it's about 10. And so I chose my gamma to be 10/3 as the recipe is telling us. And so, as I said, this is the result. So how would I use this result now? Remember, we had this at the beginning. I had this quality of life map, and so we can ask, how do we represent the data in a 2-dimensional mesh so that it is sort of compelling? And so here is one way of showing it. So what I use here is so-called button plot. So what I do is I draw a circle around each lattice point. Okay, so these buttons are just disks around the lattice point. I have a 10 by 10 lattice, and so when I have found this final organization of my prototypes, then for each data point, I'm finding the best matching unit, and I'm drawing a dot in that circle that corresponds to the best matching unit. So suppose I'm looking at one green point here. So the green point is close to one of these prototypes. That prototype corresponds to one of these circles. I'm plotting a random dot in that circle. So random, why I'm plotting random dots here. So I'm positioning the dot in this circle randomly. That's because if I plot them in the same place, they will be plotted one on top of the other, and I don't see how many data points I have in each one of these circles. So I'm distributing them randomly inside these buttons, and so that avoids me from plotting them one on top of the other. So I see that there are several green dots in one button here. There is just one blue dot in this button, etc. So, and there's an empty button here. So there's one red prototype which has no data point as the nearest. So for which this is not the best matching unit for any data point. So that's what it's saying. What is important in this plot here is that this reveals the topological structure of the data in a 2-dimensional plot. So you see that green is neighbor to blue, and blue is neighbor to red. And indeed, this is the case in the data space. So green is neighbor to blue and blue is neighbor to red. So here we are having the data in a 3-dimensional space, and I can go and look at that. But suppose I am in 100-dimensional space, so I don't have this luxury of going and look at my data. So it is very hard for me to figure out how the data are organized in that high-dimensional space. But if I do this button plot, this button plot tells me who is neighbor to who. And so this gives me an idea of the organization of the data. And so that's what the self-organization means. So now with this explanation, you may understand what this plot here is doing. So the 2-dimensional mesh in this example was chosen so that you have a hexagon around each prototype. Okay, so instead of using these circles, you use hexagons, and then you're color coding your hexagons. So it is up to you to decide how you choose the color coding. So here is some color coding. I don't know what this color coding is based on, but you can choose a color coding here. And now you are taking each country, and each country has the best matching unit. So you place that country in one of those hexagons. So for instance, let's say we have where is let's go, for instance, Japan here. So you take Japan, the data of Japan, then you find what the best matching unit for the data of Japan is. And then you go to this lattice here, and you say, okay, so this lattice point corresponds to the best matching unit that is closest to Japan. So you write the name of Japan in this hexagon. And then when you're coloring the map, the world map, you are using this color code to draw Japan with that same color. So what that does is it gives you a visual representation of the world map, so that countries which are colored by the same color, they are close to each other topologically. So this is the data organization that you are seeing here. And so this is how this organization is done. So you are just moving the prototypes and using the topology of the mesh to get the organization of the data. So here is an example, which is a remote sensing application. We have time to do this. So hyperspectral imaging. What is hyperspectral imaging? You have a device like a synthetic aperture radar, which is operating on several wavelengths. And instead of making just one image of the ground, well, this is really an infrared sensor. So let's not talk about radar. So this is an infrared sensor. So you're looking with an infrared sensor the ground, and you're looking at the upwelling radiation from the ground. So the sun is heating the ground, and different materials are radiating differently. Okay, so you want a map that tells you what material each pixel in your image is, and you're using the fact that each pixel has a different upwelling radiation pattern. So what you're doing, you're registering the upwelling pattern in different wavelengths. In this case, from 400 nanometers to 2,500 nanometers, and you are using 220 different wavelengths here. So what you would like to do, you would like to make a map based on this hyperspectral imaging that is coloring pixels which are close to each other in the spectral sense with the same color. So that's our goal. So we would like to organize our hyperspectral images so that you get one single image that tells you which pixels are of similar material. So here is an example. So this is I downloaded this from internet. So this is called the Indian Pines dataset. It's somewhere from North Indiana. And so here is a grayscale picture. So this is one single spectrum image of what the device is seeing. And so I have picked 3 pixels from here, this red pixel, blue pixel, and green pixel. And on the right, you see the spectral data coming from each one of these pixels. So this red pixel is emitting radiation with different wavelengths that is shown in this red curve. The green one is corresponding to this green curve, and the blue dot is corresponding to this blue curve. So you see that these three spots here in the map, they have a very different or relatively different radiation pattern. So my data consists of a matrix where the number of columns is the number of pixels. So I have 145 by 145 pixels. So this is the number of data points. And each column in my data vector is this spectrum of that corresponding pixel. So for instance, I take the column that corresponds to this red pixel, and in that column I have the values that I have plotted here, which are the upwelling radiation intensities with different wavelengths. And so obviously we can think that if you have two pixels which have the same material, which are of the same material, their upwelling radiation must be similar. And so those data points should be close to each other. Okay, so how can I use the self-organizing maps here? I am defining a triangular lattice. So instead of rectangular lattice, I'm defining here a triangular lattice. So I'm taking a triangle. Here is my triangle. I'll show you first. So each black dot here is a lattice point here. So then I'm defining a color coding of these points. So what I'm doing here, I'm using the RGB color coding. So RGB color coding means that you give three numbers between 0 and 1. And the first number gives you the intensity of red. The second number gives you the intensity of green, and the third one the intensity of blue. And so if you put them together, you get different colors. Okay, so I'm parameterizing my triangle using the barycentric coordinate C1, C2, and C3, which tells me that the point Q in that triangle is a linear combination of the vertices. Okay, and these CI's are the barycentric coordinates, and they have the property that they are between 0 and 1, and their sum is equal to 1. So each point is a convex combination of the corner points in a triangle. And so then I'm using RGB coloring so that C1 gives me the red, C2 gives me the green, and C3 gives me the blue intensity. Okay, so now I have a setting so you see here's a pure red, here is a pure green, and here's a pure blue. And so these are my lattices. So this is the topology. And so then I start my SOM. And so I let the prototypes navigate in this data space where I have the wavelength data of the map. And once I have decided where the prototypes are, I'm coloring each pixel according to the color of the nearest best matching unit. So if you have a data point which is close to this prototype is nearly red, so the pixel inherits the same color of the prototype. So I'm coloring the data point with that red because that's red is characteristic to the prototype. And so so my data is the radiance spectrum in jth pixel. And I run the SOM algorithm, and I attach the RGB vector by reading the barycentric coordinates of that best matching unit, and then I'm coloring the pixel according to the RGB of that best matching unit. And so here are the parameters that I was using in this example. Again, perfectly from the textbook. And so here is the result. So I was really surprised how well this works when I saw this. So here you see that there are pixels, and so you can go to the website of which is describing this INdAM Pines data. So you see that this data is rather meaningful in the sense that the cultivated land, which is I think it was corn, is colored by one color, and then there are cultivated areas which are cultivation of I think alfalfa or soybean or something, and they get a different color. So looking at this map, you can tell what is in the map. So instead of this highly complicated hyperspectral data, you can take one single snapshot using this self-organizing map image, and you see immediately where in the map you have similar cultivation. And so that is one way of using the self-organizing map. I think this is my last slide for today, and so it is 5 o'clock, perfect. So we finished the self-organizing map. I may give you later one more example of self-organizing maps when we are talking about image mining. But so this is basically what you need to know from self-organizing maps to be able to implement them. And so they are easy to implement, and it's very sort of a versatile platform to visualize data. So that's the strength of the self-organizing map. I thank you for joining today, and I hope you have a nice weekend, and we'll see on Tuesday again. Thanks, everybody.
Okay, thank you.
Thank you.
Thank you.
Thanks, Professor.
Grazie, arrivederci.
Thank you.